Today, lesson 24B, day number 1 of scientific notation. Now, I know in science, you guys have done the basics of converting back and forth between big numbers, small numbers to scientific notation, and then taking numbers that are in scientific notation and taking them out, which is referred to as standard form. But in this class, our focus is doing numeric operations with numbers that are in or maybe not in scientific notation, maybe converting back and forth between those things. So that will be our focus over the next couple of days. So, a little background knowledge. A number is typically in scientific notation, and that's sometimes referred to as normalized scientific notation. If we have some number between 1 and 10 times some power of 10, where the power of 10 is an integer, and that's basically what that definition means. And so I know all of you guys know how to do this. We have this number, and if we want to convert it to scientific notation, we have to turn it into a number between 1 and 10, which is 6.32, and then we need to figure out what the power of 10 is. I always have thought of it this way. If we started with a large number, a number bigger than 10, the exponent should be positive, and if the number is smaller than 1, like the second one is there, then we would have a power of 10 that would represent a negative number. Remember, the exponent is always how many times you move the decimal. And we've all done this in science, correct? Yes or no? Yes. All right, so have we, well, I guess before I go on, scientific notation is one of the few situations in math or science where we're allowed to leave answers with negative exponents. Because before today, I have continually made the statement in math, typically we don't leave things with negative exponents. Scientific notation is one of those situations where we do leave answers with negative exponents. So the purpose of scientific notation is a way to write very large or very small numbers in compact form, like this large number. It's a lot shorter way of writing or representing the same or a similar number, or perhaps the size of a hydrogen atom, very small, but in scientific notation it looks like that. Have you guys worked on taking numbers out of scientific notation? Yes? Okay, so we all know that we need to take 3.41 and move the decimal 6 places to the left? Yes? How do you know whether to move to the left or to the right? Is that how you remember it? Okay, and that's fine. I've always remembered it as something like this. If the exponent on the power of 10 is negative, that means we have to make the number smaller, and the only way to make 3.141 smaller is to move the decimal to the left. Same thing if we have a positive exponent for the power of 10. That would mean we would need to make the original number bigger, so we would have to move it to the right. But whatever it takes for you to remember how to write numbers in standard form. Standard form is taking a number out of scientific notation. So we've got the basics of scientific notation down, but what if you were asked to multiply two numbers in scientific notation, like this problem? Well, there are many reasons in math why we have properties, and one of the properties that we use frequently is the commutative property, and it allows us, if we have a straight addition or straight multiplication problem, to rearrange numbers. So if I take this 2.1 times 10 to the 8th and multiply that by 1.5 times 10 to the 6th, if I regroup things, put the 2.1 and the 1.5 together, and I can do that because this is straight multiplication, and put the powers of 10 together, the reason why that's a little easier to deal with is because we can quickly multiply 2.1 times 1.5, and then since we have two numbers with the same base, we can add those exponents. And that is the commutative property that allows us to do this. So 2.1 times 10 to the 8th times 1.5 times 10 to the 6th turns into 3.15 times 10 to the 14th power. And I know that this problem and the next problem is totally worked out for you in your notes. So on the next one, I'm going to go about this the same way. And since it's already in your notes, I'm going to go quickly. I'm going to do a little bit of regrouping here using the commutative property. 5.63 times 3.4 is 19.142. Since the powers of 10 have the same base, I can add the exponents using that exponent rule. And so that would leave me with 19.142 times 10 to the 15th power. But this number is not in scientific notation. And it's not because 19.142 is not between 1 and 10. So if I want to put this in scientific notation, obviously on the 19.142, I need to move my decimal to the left one time. That's dividing it by 10. So what I've done is I've made that number smaller by a power of 10. So that would mean to counterbalance this thing, I would need to make the exponent 1 larger by a power of 10. So that means increasing the exponent by 1. So what we need to make sure that we do is we need to make sure that our answers are in normalized scientific notation. So that would be 1.9142 times 10 to the 16th. All right, any questions about either one of those problems? All right, I want you to do number 4, 5, 6, and 7. Go ahead and do all 4 of them, please. Number 4, we regroup the 8 times the 1.2, that's 9.6. Add the exponents on the 10s because the base is the same, and that's what we do when we are multiplying exponents. Can I leave my answer like that? Yes or no?
Yes.
Yes, that is in scientific notation. Number 5 looks like this. We regroup the 2.4 and the 4.9, multiply those two, and then the powers of 10 together. That would give us 11.76 times 10 to the 16th power. Can I leave my answer like that? Yes or no? No, that is not in scientific notation. Remember, this first number has to be between 1 and 10. And it's not. So what that would mean is that I need to make the 11.76 smaller by 1 power of 10. In other words, make it 10 times smaller, which would mean I would need to make the 10 to the 16th. By counterbalancing that, I would have to make that bigger by a power of 10. Now I have something in scientific notation. 1.176 times 10 to the 17th. Same thing in number 6, regroup. We have something not in scientific notation, so now we need to put it in scientific notation. 2.405 times 10 to the 19th power. And then number 9, same idea. When we have negative exponents, we have to be a little more careful. In other words, we have to think about it a little more. Because a power of 10 bigger than 10 to the negative 11 is not 10 to the negative 12th. It is 10 to the negative 10th. Any questions about those 4? All right, so now we shift our focus to dividing numbers that are in scientific notation. And this works really the same way, and it looks similar to ways that I was approaching some dividing or division exponent problems last week. I'm going to break it up into the 9.1 divided by the 3.5, and then the 10 to the 12th over 10 to the 7th. And when we have things with the same base, when we have expressions with the same base and we are dividing, we can subtract exponents. So 9.1 divided by 3.5 is 2.6, and so that would be 2.6 times 10 to the 5th. And like multiplying, it is the commutative property that allows us to do that kind of thing. Sometimes what we get is already in scientific notation and sometimes not, like in the second one here. So we break this up. 4.3 divided by 5 is 0.86. And then we subtract the exponents because we have a division problem with expressions of the same base. So now I need to make the 0.86 bigger by 1 power of 10. Why? Because that's not between 1 and 10. And if I'm going to do that, then I have to make the other expression smaller by a power of 10. You have to do the opposite to sort of keep it balanced if you want to think of it that way. So it should be 8.6 times 10 to the 11th. All right, everybody please do number 8 and number 9. All right, so obviously this is not anything that's overly complicated. The only comment I have to make is I saw a couple of you when I was walking around. You left number 9 like this. That is not in scientific notation. The very first number has to be between 1 and 10. 0.69 is less than 1, so that means we have to do a little more work to make sure that that is in scientific notation. So it should be 6.9 times 10 to the 11th. Any questions on 8 or 9? All right, next problem. Please order those from greatest to least. I'll give you about 1 minute. One way about going about trying to figure out the order of these things would be to think of them in standard form and then just start comparing each digit as we go along there. Right now they're even, they're still even, they're still even, they're still even, and finally we can easily see that 4.3 times 10 to the negative 4 is the largest, and then go to the next column and we can see that 3.4 times 10 to the negative 5, and I know that there are other ways of figuring out the order for that. But that leads us to our last idea for today, and that is this. The question is approximately how many times bigger is this number, 4.3 times 10 to the negative 4, than this one right here, 3.4 times 10 to the negative 5. And we're going to go about that utilizing something that we just talked about a couple minutes ago. If I were to ask you this question, how many times bigger is 6 than 2? We could all answer that question. Well, how many times bigger is it?
3.
And how do you get that? How do you get that?
2 times 6.
Well, I think of it as something slightly different than that. Alicia?
Divide 6 by 2.
Yeah, 6 divided by 2 quickly tells you that 6 is 3 times bigger than 2 is. So if we use that same sort of rationale, and this is a problem that we just did a few minutes ago, how many times bigger is 8.4 times 10 to the 19th than 2.1 times 10 to the times 10 to the 5th? It's very simple. If we use the idea of division, that's one of the reasons why we have division, we can quickly figure out that 8.4 times 10 to the 19th is 4 times 10 to the 14th times bigger than 2.1 times 10 to the 5th. So now, let's go back to this question that I just asked you. Approximately how many times bigger is 4.3 times 10 to the negative 4 than 3.4 times 10 to the negative 5? Figure that out, please. We utilize the idea of dividing numbers that are in scientific notation. Split it up. Do the division 4.3 divided by 3.4. I rounded it so that I didn't have to write a very large number. And anytime we end up with something like that, it's okay to round, in this case, the 1.26, whatever it is, to 1.26. And that would give me 1.26 times 10 to the first. But we do need to convert that to a number so it makes a little more sense. So 4.3 times 10 to the negative 4 is approximately 12.6 times bigger than 3.4 times 10 to the negative 5, because this in standard form is 12.6. All right, any questions? All right, we are finished.